In this question, we know the random variable x and random variable y are independent, and we also know the probability density function of random variable x is equals to this, and the random variable capital Y, and the probability density function of random variable y is equal to this, and z is equals to x plus y, and because x, y are independent, so using the conclusion of convolution method, we can using the conclusion of convolution method, we can know that the fz z equals to f x z convolutes f y z, and it equals to the integral from minus infinity to infinity f x alpha multiple f y z minus alpha d alpha, and we can and because we have already known the probability density functions of x and y, so we can substitute the alpha and z minus alpha to the x and y, so we can obtain this fz z equals to the integral from minus infinity to infinity u alpha minus 1 minus u alpha minus 2 and multiple u z minus alpha minus u z minus alpha minus 1 d alpha, and we can continue to calculate this part, and we can write the integral into this format. U alpha minus 1 multiple u z minus alpha and minus u alpha minus 2 u z minus alpha and minus u alpha minus 1 multiple u z minus alpha minus 1 and plus u alpha minus 2 and multiple u z minus alpha minus 1 d alpha, and we can write this part into 4 parts integral, which is equals to u alpha minus 1 u z minus alpha d alpha, and integral from minus infinity to infinity u alpha minus 2 multiple u z minus alpha and minus this should have d alpha and minus the integral from minus infinity to infinity u alpha minus 1 multiple u z minus alpha minus 1 d alpha, and the last part is the integral from minus infinity to infinity u alpha minus 2 multiple u minus z minus alpha minus 1 d alpha. And the first part and we can find that the upper limit is z, the lower limit is 1. And because the stat function's value is 1 when it is in its definition domain, so this should equals to 1 multiple d alpha multiple u z minus alpha. And this is the first part. And the second part can use the same method of the first part, which should equals to the integral from 2 to z 1 d alpha multiple u z minus 2. And the third part can also be calculated using the same method as first part. The lower limit is 1 and the upper limit is z minus 1. And so multiple u z minus 2 using the upper limit minus the lower limit, and the last part is z is 2 z minus 1 d alpha u z minus 3. And it is because that the x is between 1 and 2. The y is between 1 and 0 and 1. So the z is obvious between 1 and 3. And so it is obvious that this part should equals to z, because the z is between 1 and 3. And so this part is equals to 0. And so it is should equals to z minus 1 multiple u z minus 1 minus 2 z minus 2 u z minus 2. And then we can draw the figure of fz the random variable fz z. It is obvious that when z is smaller than 1, the fzz should equals to 0. And when z is between 1 and 3, and it is obvious that the figure should be this. And when z is more than 3, and because the random variable z is between 1 and 3, so when z is younger than 3, it should be equals to 0. So this is the first question. In the second question, we are required to use geometric method. And first, we can let f x prime equals to u x prime minus u x prime minus 1, and fy y equals to u y minus u y minus 1. And we can and we let z prime equals to x prime plus y. And so we can draw the figure of x prime and y. We can also draw the line of y is equals to z minus x prime. And it's obvious that this point is z prime. And it is obvious that when the line is in the square, the probability should equal to the probability of f z prime z. Using the definition, it equals to the z prime is smaller or equals to z prime, and which should equals to x prime plus y smaller or equals to z prime. And it is obvious that when the line is in the square, this probability should equals to the area of the sheet. And using the figure, first, when z prime is smaller or equals to 0, it is obvious that in this circumstance the probability distribution function of z prime should equals to 0, and so the probability density function f z prime should equals to 0. In second circumstance, when z is between 0 and 1, it is obvious that in this circumstance the fzz should equals to the area of the sheet, so it is equals to 1 divided by 2 multiple z prime to the power of 2. And so we can calculate the probability density function of z prime. Should equals to z prime. In this third circumstance, when 1 is between z or z prime, this place should be z prime and y between 1 and 2. The f in this circumstance we draw a line, and this point should equals to z, and so this part, and because this angle is 45, so this part is equals to this part, which is equals to z minus 1. So this part should equals to 1 minus z minus 1. And also because this angle is 45, so this part is also equals to 1 minus z minus 1. And so, and because in this circumstance the probability is equals to the sheet area, so in this circumstance the sheet area should be 1 minus z minus 1 to the power of 2 multiple 1 divided by 2, and the result is minus 1 divided by 2 multiple z prime to the power of 2 plus 2 z prime minus 1. And we can calculate the probability density function of z prime, which should equals to z prime is equals to minus z prime plus 2. In the fourth circumstance, when z prime is bigger than 2, it is obvious that in this circumstance the z prime is equals to 1, and so the probability density function of z prime is equals to 0. And so we can write the analytical format of z prime, the probability density function of z prime is equals to the first part when z prime is smaller or equals to 0, which should equals to 0. And when z is between 0 and 1, it should equals to z prime. And when z prime is between 1 and 2, it should equals to minus z prime plus 2. When z prime is bigger than 2, it is obvious that it is equals to 0. And because the f(x)(x), it is equals to ux minus 1 minus ux minus 2, which should equals to the f(x) prime minus 1. And so we need to shift the result the result of x prime to the right side. Right side by 1, so that we can get the analytical format of fx random variable x and the figure of x. So the fz so that we can get the result of fz prime. We need to shift the result of fz prime to the right side by 1, so that we can get the result of random variable z equals to x plus y, and the fz and it equals to 0 when z is smaller or equals to 1, and z minus 1 when z is between z and 2, and 3 minus z when z is between 2 and 3, and 0 when z is bigger than 3. And we can also draw the figure of random variable z, which is obvious is the figure of random variable z prime, and this figure move to the right side by 1, we can get the figure of random variable z, which is this. And so we can find it is obvious that the second question's result is the same as the first question, and we just use the different method to calculate the result of random variable z. In the second method, we use a random variable z prime and x prime, so that we can calculate the the probability density function of random variable z more conveniently. So this is the first question.